Hi guys, welcome to my YouTube channel. Today I'm going to talk about isotopes, and that's um, the topic or the discussion is going to be focused on the nucleus of an atom. So let's go to the periodic table and talk about some of those atoms that are going to be um, uh, radioactive. Okay. As we move on from hydrogen is just a proton, the nucleus of hydrogen. As we move on to heavier and heavier elements, we got more and more neutrons involved. And as you can see in this figure here, the nucleus itself is not something that is like a static waiting there, but it's like there is still jiggling, wiggling between those protons and neutrons. Protons has been shown here in red, and neutrons has been shown in blue. Neutrons has no charge, protons has positive charge, we know that. And protons in the periodic table, it's sort of, it starts from one proton here, two protons, three, four, all the way to 118 protons. That gives you all the elements. So when you change the number of protons, you essentially change the atom. Like if I go from three protons, which is lithium, to four protons, that would be another atom. It won't be, we can't have a lithium with four protons. Four protons would just mean beryllium. But if you change the number of neutrons, because neutrons are neutral, they're not going to give different elements. So three protons with one extra neutron could be another lithium, another isotope of lithium. So they're chemically, like chemistry is all important about electrons and protons. Okay, then they have to cancel out. So if you change the protons, the chemistry will change, but neutrons, if you change that, it would have the same element, you would have the same element, but we call it a different isotope. Okay, so let's talk about real cases. I am interested about PB, and for any symbol, any atomic symbol that we do, on the top here we have a number that we call the mass number, and that's, we show it with a number that is the combined number of protons and neutrons. So P, let's just use the same symbol that we see on the screen, jiggling and wiggling as nucleus. So that's the combined number of all protons plus all neutrons. Okay, and down here we have an atomic number. An atomic number, I just explained, when you add protons, you're going to chemically define another element. So this is the pure sheer number of the protons. Okay, so that's how you designate this on a symbol for an element. So you have the symbol for element. Symbols for elements are a big letter, a capital one, and then a small letter. So this is actually if they're two letter coded. If you have just P, that would be phosphorus, but PB is lead or plumum. So, and I told you that the previous time, that it comes from plumbing, ancient Greeks. So that's protons and neutrons on the top for your mass number, and for the atomic number, that's only the number of protons. So if you have this number and this number, you kind of know how many neutrons you have, how many protons you have. And if you have the charge, which in this case is just zero, I could actually get the electrons to be exactly the same as the number of my protons. If you have positive charge, then the electrons are less, to the extent of that you have positive charge. And if you have negative charge, the electrons would be more than protons. That would make, because the electron is negatively charged. Let's talk about specific examples here, so that we could actually move on to actual problems on isotopes. So PB 4 plus, sulfur double minus, and Cu plus. And let's say this is 208 and 82, 34 and 16, 63 and 29. And the problem is asking for the number of protons, the number of, let's do electrons with another color. Let's just use orange. Number of electrons, and then the number of neutrons. Okay, let's see if you could all see the number of electrons here, because I can see it here, but I have to look back at my camera to see if you all can see the electron that I put here. So the number of electrons as well. Now you could see it. I could make sure that you all can see it. Now let's move on to the problem. So the number of protons is obviously 82. Because it's plus 4, it has to has 4 less electrons to make it a positive 4 plus. Okay, so that's going to be only 78 electrons, and the number of neutrons just this minus that, and that gives you 126 neutrons for this one. For S, the sulfur, which is double minus, by the way, sulfur double minus is called sulfide, and we kind of have rules for knowing these anions of main elements, okay, and we'll talk about that when we talk about naming of anions and cations, okay. So on this one, if you could see, the number of protons is determined right from that number. The number of protons is 16. The number of electrons, 2 more electrons, so you add 2, and that's 18, and 34 minus 16, and it will give you the number of neutrons. Oh my bad. Let me just quickly catch up that marker and put up the 18, which is the number of neutrons as well. Okay, so for this one, that would be the exact same story. 29, my bad, is the number of protons. If it's plus 1, it means it has 1 less electron to make it positive 1, so 28 electrons, and that minus that, or 63 minus 29, that gives you 28 neutrons. So that's how you count the number of protons and neutrons if you have a species and if it's charged. If it's not charged, the number of electrons and protons, you just they have same number of electrons as they have protons. Okay, let's now move on to cases where you want to deal with the atomic mass. Okay, the atomic mass of any of these small jiggling wiggling subparticles or atomic subparticles, protons and neutrons, so to speak. Again, protons, we take them as these red spheres, and neutrons, we take them as those blue spheres that you could see. The mass of those two particles are exactly the same, just that the red ones, or the protons, have positive charge, and neutrons, just as the name implies, are neutral. Okay, so they don't bear any charge, but the mass is 1 AMU, or is equivalent of atomic mass unit, and it's something 10 to the negative 27 kilograms. So very, very small, even smaller than the Avogadro number. That would 10 to the 23, and this number is even smaller, and actually the 1 AMU is actually much more smaller compared to kilogram. Okay, if you also compare with Avogadro is a huge number, that's 10 to the 23, but if you 10 to the 23, if you compare the orders, this one is even more huge in terms of orders. That's 4 orders, how to say, 4 orders more magnificent, or more how to say, more zeros compared to the Avogadro number. Okay, more places. So let's talk about the atomic mass. Okay, now if you have an atom, like, let me talk about hydrogen real quick if I have time. Yeah, I do. Hydrogen is the only one that its elements, like its isotopes, has different name. You could have a hydrogen that has just 1 proton and 1 neutron. My bad. No neutron and 1 proton, that's the normal hydrogen. If you have just one of those blue particles, 1 neutron, then you would have 2, because 1 neutron, 1 proton, and we call it deuterium. And if you have 2 neutrons, that would make the atomic mass, the mass number 3, because there are not 2 protons, and we call it tritium. For all the others, we just actually say a different isotope, the same name, just we say this number, the mass number, to distinguish between them. Okay, now let's imagine a simple example of chlorine. We have a chlorine 35 and a chlorine 37. Okay, it means the total number of protons for this is 35, and total number of protons and neutrons for the other isotope is 37. They have both the same number of protons, by the way, and this one has two more neutrons. Okay, because if you change the protons, that would not be a cold ring anymore. So these are how we show the two isotopes. Let's say we have the masses of each one of them, and the masses there is a very good thing about the masses of this in exact AMU. If you don't have that, you could safely assume that it's 35.00 AMU, but let's say the problem actually tell us that mass that is 35.9689 AMU, and for 37 that's 36.9659 AMU. Let's say if you have those two masses and you are going to work out the the atomic mass. The atomic mass that you could see on your regular periodic table, that says, if you could see here, it says 35.45. That can be found if you have the percentages. Okay, and let's see, the problem tells you the percentages are, for this one it's 75.77%, and for this one the percentage is just 24.23%. You have to just convert the percentages to fractions. It means dividing them by 100 so that you have a fraction, and then times this fraction times the mass of its isotope. That would be the mass contribution from this lighter so-called isotope, and also the fraction of this times that, which gave you the exact mass contribution from the heavier isotope. Okay, so let me just write that down here on the top to find out if we could find that number. That means, let me get another number, another marker, another color. So 34.9689 times 0.7577, that's the fraction. I just divide this by 100. Okay, so actually moving the decimal place 2 places, plus this times this, that is the mass contribution of the heavier isotope. So that's 36.9659 times Q4Q3. This will give you a number that is 26.49594, plus this one will give you a number 8.95684, and if you add them up you will find this number. Okay, you will find 35.4. You'll find exactly 35.45. A little bit more numbers because we have more of those decimal places. Usually when you do work with isotopes, 4 or better 5 decimal places, 5 orders after the decimal place is the best to work with. Okay, now let's move on to another example. So I worked out, if I have the masses of both light and heavy isotope and I have the percentages, how could I work out the mass, the atomic mass, that is the same one that is shown up in the periodic table, and we could check that right here. Okay, now what else? Can I do the reversing? Then it's a little bit harder, but I wish to do that at least once so that you can also follow what's going to, what a problem like that should look like. Okay, so let's just get the board a little bit more clean. Actually, if I take it a little bit down here. Okay, my bad, sorry for the interruption. Okay, now let's move on to a problem. If I told you the problem is 2 isotopes of rubidium is Rb, again capital and small, and if you have just one letter, it could be also another atom. I can't recall if we have any element that is just R. We do have Rb, Re, and some other elements, but Rb is rubidium, and that's from the first group. And as you move to the third section of your learning process, memorizing process, you should also memorize this element from group 1 main group. Rubidium 85 and rubidium 87, lighter isotope, heavier isotope. Again, there's only 2 protons for this isotope, 2 neutrons more for this isotope. And if you do know that the weight for this is 84.9118 and the weight for this is 86.9092, again, AMU is the unit, atomic mass unit, and you know that the mass of rubidium is 85.4700. Also, you could find it here on the periodic table. Rubidium is 85.4700. Okay, 00 is actually not shown, but since I have more accurate measurements, I'm going to actually take this one more accurate and then going to calculate percentages here. I do assume a fraction here, x, and a fraction here, y, and x and y, if they're just fractions, should be equal to 1. Okay, and I do know that the fraction of this times the mass of the lighter isotope plus the fraction of heavier isotope times its mass should be, if I add those two numbers, should give me this number. Okay, now how do I do that? Let me just write it down. Let's take another marker and see if we could write it a little smaller, because this one is better a little bit. 84.9118 times x plus 86.9092 times y is going to be equal to 85400. Now to do this, I need to actually split this to the same amount of y, the bigger number, the bigger atomic mass unit, to the exact same amount of this, and then the remaining. Okay, and that would be to split this. So I just put down the same thing for y. I just say 84.918 x plus. Now for this one, I would like to split it to 2 components, and that would be 84.9118y plus, and the remaining, actually I add the remaining to get that 86 exact that, so that would be 1.9974y equals 85.4700. Now if you look at this and you look up here, x plus y is just 1, so I could actually factor out this number and say 84.9118. Let's see if it's visible here. It's not that much visible, so I would just like to move a little bit to this place. 84.9118. That's the exact same number. This blue number here and this black number are exactly the same. I just factor it out. So times x plus y plus 1.9974y is equal to that same number. Okay, so let's use up this space here to move on. So I used the relationship of x plus y is equal to 1 to make this one simpler, and that would be just 84.9118 times 1, it would be itself, plus 1.9974y equal to 85.4700. And if you look, now you have only y here in the equation. This much y plus this is this. So you take 85, you put this to the other side, that would be this minus that, and you would find out that 1.9974y is 85 minus 84, and that would be 0.5582. And if you just take this and divide it by 1.9974, you get what y is. And then y would be, you could see that y becomes 279, and x then becomes, because x plus y, remember x plus y is just 1, so 1 minus that number would give you the other fraction, that is 71. Okay, and if I just multiply them by 100, so I can find the fraction. Now the fraction of my heavier isotope, that was, I assumed it for Y, it was the rubidium 87, that was Y and this was X. So my Y is 27.9%, or this one is 27.9%, and for X I could see that this is 72.1%. 72.1%. So that's how you do the calculation in reverse steps. If I do have the weights of my heavier isotope and lighter isotope, and I want to work out the percentages, okay, I just take X and Y. You assume them as fractions, that X and Y will become collectively, instead of 100, it's easier to just assume them as fractions, so that X and Y is equal to 1. Okay, so that makes the calculations a little bit easier. And then we just say the same formula that we used: the fractions times the mass of my heavier isotope plus the fraction times the mass of my lighter isotope would be equal to the 85.47. That is the average atomic mass. Now the average atomic mass is what you have in the periodic table, and if you look for rubidium, again you could find that this is the average atomic mass, and the average is 85.47. So I want to wrap it up here until the next